Hi guys, so today we're going to look at how to graph the majority of rational functions. So to start, we just looked at some transformations from the parent function, but those are really just the most simple examples. Today we're going to look at some more complex rational functions, and we're going to look at how to find the asymptotes and intercepts, as well as some special cases that involve holes and slant asymptotes. So to start, we're going to look at just how to find the most important features. Those are our asymptotes and our intercepts. Starting with vertical asymptotes, we talked about this already. Vertical asymptotes occur when we have a number divided by 0. So in order to find that, we set the denominator equal to 0. And that's how we find our vertical asymptotes. There could be one, there could be more than one, there could be none. It just depends on the function that you have and what's in the denominator. And remember, this occurs because a number divided by 0 is undefined. Horizontal asymptotes are a little bit different. So with horizontal asymptotes, we really have three possible cases. So what we do in order to figure out our horizontal asymptotes, so with these cases, what we do is we look at the degree of the numerator and the degree of the denominator. So three things could happen. One is we could have a higher degree in the denominator. If that's the case, we'd call that function bottom heavy. So if the degree on the bottom is bigger, then our horizontal asymptote is just y equals 0. If the degree on the numerator and denominator are the same, then what we do is we divide the leading coefficients. So we would get something like y equals whatever that leading coefficient is over the other leading coefficient. If our function is top heavy, there is no horizontal asymptote. But there is a special case if the top is exactly 1 degree higher than the bottom, then we're going to have a slant asymptote. And we're going to get into slant asymptotes here in a little bit. We have a whole section on it. But that takes the place of the horizontal asymptote. We're not going to have both. X-intercepts, if you remember, X-intercepts are what we do when we solve the equation. We set the equation equal to 0 and solve. So like on a quadratic, we found the x-intercepts by finding the zeros, finding the solution, setting it equal to 0 and solving. Same thing for rational functions, but what's nice, as long as you get 0 at the top, 0 divided by anything is still 0. So all we really need to do to find our x-intercepts is set the numerator equal to 0. Then for our y-intercept, we find that the same way. We will always find y-intercepts for every function we do throughout the year. You plug in 0 for x. And those are really the four key features. Now, there's a few special cases with some extra features, but these are the four main things we need to get in order to get an accurate graph. So to start, let's just go ahead and do horizontal asymptotes. Again, look at the degree of the top and the degree of the bottom. Well, in this case, the top degree is 4 and the bottom degree is 4. In that case, I divide the leading coefficients. So my horizontal asymptote is y equals 4. If you look at B, this is a higher degree on the bottom because the top is a second degree, the bottom is a third degree, and if it's a higher degree on the bottom, it's just y equals 0. So now let's look at some examples where we have to do all of these steps. All right, so starting with the first one, this one's still pretty simple, and we're just going to go through and find all these components. Vertical asymptote, we set the denominator equal to 0 because we can't divide by 0. So I get x equals 1 for my vertical asymptote. Then I move on to the horizontal asymptote. For the horizontal asymptote, I look at the degree of the top and the bottom. Well, in this case, they're the same degree, so I'm going to divide the leading coefficients, so I get y equals 2. Now I'll do my intercepts. We'll start with the x-intercept. Because 0 divided by anything is 0, the x-intercept would be 3 over 2, comma 0. So I'm going to go over to 1.5 and mark that point on my graph. Then we'll do our y-intercept, plug in 0 for x, and if I plug in 0, that gives me negative 3 over negative 1, so I get 0, 3 as a y-intercept. Now at this point, we just need to sketch our graph in the right quadrants. Well, to the left of my vertical asymptote, I have two possible sections, one above and one below the horizontal asymptote. I know my graph needs to approach both asymptotes. I also know I have to pass through the y-intercept. And since the y-intercept is in that top quadrant, this first curve is going to go in the top quadrant. The second one, again, we have an x-intercept down below. I have to approach both asymptotes. So in this case, this curve is going to be in the bottom quadrant. And then again, it's just going to approach both asymptotes. Another thing we talked about in class, if a factor is squared, then at that asymptote, your graph is going to go in the same direction. But in this case, because that factor of that asymptote is to the first power, our graph is going in opposite directions. All right, let's look at our next one. We're going to factor first. That's always our first step. Even if we only need one component, we always want to factor the top and bottom first, because later we're going to see some cases where there's some holes and some things that cancel out. Well, now that this is done, I can see that there's a vertical asymptote in two places, both at x equals 3 and at x equals negative 3. Then we'll go to our horizontal asymptote. In this case, the degree is higher on the bottom, which means our horizontal asymptote's at y equals 0. Then we do our intercepts. To find the x-intercept, I set the top equal to 0. And then to get the y-intercept, I plug in 0 for x. And this is easier if you use the non-factored, because then I can easily see it's just 0, 1/9. So now at this point, the sketching of the graph is really the hard part. But at this point, you've gotten a lot of components. What's really hard to figure out is what's going on really in this middle region right here. And we saw some examples in class of a lot of different things this graph can do. So we have a few options. We could use what we know about the information given, or we can also plug in test points to see what our graph is doing to help us make a decision. If we pick test points, we need to pick test points that fall within the regions in between the x-intercepts and the vertical asymptotes. So in this case, if I were to pick test points, I have 4 regions. I have one region here. I have one region until that x-intercept. I have another region here. And then I have a region over here. So on this one, let's just go ahead and start with test points. So if I pick a test point in the yellow region, like negative 4. If I plug in negative 4 to the factored form, negative 4 minus 1 is a negative number. Negative 4 plus 3 is a negative number, and negative 4 minus 3 is a negative number. That means everything within that region is going to be negative, because the only place I can cross the x-axis is either at a vertical asymptote or an x-intercept. And in that yellow region, none of those things are going to change. So that tells me that everything in that yellow region is going to be below the x-axis. So I'm going to have a curve in this quadrant. I don't know why I picked yellow, sorry guys. All right, then we'll go to that red region. Okay, in that red region, again, pick a test point. Well, I've already picked 0. When I picked 0, I got a positive number. So that means everything from that x-intercept over until that vertical asymptote is going to have a positive x value. Then we go to our next test point, that purple region. So if I pick a test point in there, like 2, plug it into the factored form, 2 minus 1 is positive, 2 plus 3 is positive, and 2 minus 3 is negative. Well, a positive divided by a positive times a negative overall is negative, which means everything in that purple region is negative. And again, I still go down towards that vertical asymptote. Now let's try the blue region for the last part. I'll pick a test point of 4. 4 minus 1 is positive, 4 plus 3 is positive, and 4 minus 3 is positive. So that entire region is going to be positive. So everywhere in that little blue region is going to be above the axis. And again, we're going towards that horizontal asymptote. And there's my graph. All right, now let's say we didn't know that information. Okay, let's say we didn't plug in our test points. We could still get a pretty accurate graph without actually picking those test points. So the other thing we can do is use the information we know about the x-intercepts and about what our graph does at those vertical asymptotes. So reviewing what we did back in polynomials, we talked about with x-intercepts, if that factor was squared, our graph would touch or bounce off at that point. But look here, x minus 1, that factor is raised to the first power. If that factor is raised to the first power, my graph is going to cross through that point. Well, I have to touch that y-intercept, so after that y-intercept, I'm going to cross through and go to the vertical asymptote. Since I'm positive at that y-intercept, we know that part's going to go up. We also know that both the vertical asymptote factors are also both raised to the first power. Neither of those factors was squared, so that means at that vertical asymptote, my graph is going to be going in opposite directions. So my graph looks like this. It's the same thing we would have gotten by plugging in test points. It's just a different way to get there. All right, so now let's look at a special case where we get a slant asymptote. So slant asymptotes are sometimes also called oblique asymptotes, and these occur when the top is exactly 1 degree higher than the bottom. Now, it is possible for the top to be more than 1 degree. It just won't be a slant asymptote. The asymptote would look like a different shape because slant is a line, and these are going to give us linear functions. The way we find a slant asymptote is we divide using the same methods that we learned back in polynomials. What's nice here, though, is that we can ignore the remainder. Because if you remember, the remainder we wrote as a fraction over the divisor, and that's going to be such a small difference on our line, it's not something we can actually graph. So we're just going to ignore the remainder when we write our equation. All right, so let's look at this example down here. Again, the first thing we're going to do is factor, just to make sure nothing cancels out. And nothing does. So let's look back at the original function. Our vertical asymptote is at x equals 2. There is no horizontal asymptote because this one has a higher degree on the top than the bottom. But because the top is exactly 1 degree higher than the bottom, we're going to use division in order to find our slant asymptote. Since we're dividing by x minus 2 and not x squared, we can go ahead and use synthetic division. So 2 is going to go in the box. We write our coefficients. And again, the remainder doesn't really affect our answer because remember, to write our answer, we start 1 degree less than the original. The original was squared, so this would be x plus 1. That means our slant asymptote is y equals x plus 1. We don't need to graph the negative 4 over x minus 2. That's not something we can graph. So on this graph, I'm actually going to graph the line x plus 1 as an asymptote. And it's going to serve the same purpose as the horizontal asymptote. It's going to show us end behavior, but it is something that you can cross. And I'll make my vertical asymptote. Then we'll do our intercepts. So again, just like last time, x-intercepts is when the top equals 0. In this case, there's 2 of them. So I have an x-intercept at 3 and an x-intercept at negative 2. Y-intercept, plug in 0 for x. Negative 6 divided by negative 2 is a positive 3. And again, y-intercept is always easier in the original. It just makes it much easier to see. So y-intercept is 0, 3. Again, this is going to be very similar to a horizontal asymptote. If you look, we kind of have these 4 little quadrants again that our graph could possibly go in. Since I have 2 points in this first quadrant, I'm going to go toward my asymptote, toward my asymptote. I have another point here, toward the asymptote, and toward the asymptote. And then I have my graph. All right, to review domain, vertical asymptotes are excluded. The x-coordinate of a hole will also be excluded from the domain. So there's my domain. Range on this one a little bit different. On this one, our range is actually negative infinity to infinity. There's nothing that stops the range here. End behavior also is going to look a little different than the ones we've done so far. As x approaches negative infinity, y is approaching negative infinity. It continues to get smaller. It does approach that asymptote, but that asymptote is approaching negative infinity. So we don't need to say that it actually approaches the asymptote. Then as x approaches positive infinity, y is approaching positive infinity. All right, so the last special case we're going to look at are removable discontinuities, or holes in our graph. So these occur when a factor cancels out. So the first thing we do, like we said, is always to factor top and bottom, because we need to make sure that these don't happen. Because if a hole occurs, it's going to change our vertical asymptotes and potentially our x-intercepts. So let's go ahead and factor the top. So this factors into x plus 3, x minus 3. And if you notice, that x minus 3 factor is going to cancel out. So if you remove a factor, it creates a removable discontinuity. For the whole, it's going to have an x-coordinate and a y-coordinate. The x-coordinate of the whole comes from the 0 of the factor that you cancel out. So if I cancel out x minus 3, positive 3 is the x-coordinate of the whole. If I canceled out x plus 7, negative 7 would be the x-coordinate. Now, after it cancels out, you'll notice we just have, the only function we have left over is just x plus 3. So from the rest of this, to graph the rest of this problem, we are just going to use the remaining function. Once it's canceled, we find the x-coordinate of the whole, and then we move on. To get the y-coordinate of the whole, I take the x-coordinate and I plug it into the remaining function. Well, if I plug that in, then I get 6. Then from this point, we can go ahead and find the rest of the features we need. But think about it, in this case, we just have, the only remaining function we have is y equals x plus 3. That's not even a rational function. So there's not going to be a vertical asymptote or a horizontal asymptote. All we have is an open circle at 3, 6, and then we're graphing the line y equals x plus 3. And that's our graph. So we can still find the x-intercept, and we can still find the y-intercept, but this graph isn't going to have any vertical or horizontal asymptotes. It's just a line with a hole in it. All right, so let's move on to B. Again, same thing. We're going to factor first. And this time, x minus 5 cancels out. If x minus 5 cancels out, then there's going to be a hole with an x-coordinate of 5. So now let's look at the remaining function. When x minus 5 cancels out, it doesn't disappear. We still have a 1 wherever we're dividing that out of. So we still have a rational function left over. So let's take 5 and plug it in. That gives me 1 over 7 for a y-coordinate. So at 5, 1/7, I'm going to have an open circle on my graph. Then we can just continue to graph the function 1 over x plus 2 the same way we have graphed all these functions so far. Let's find the vertical asymptote, the horizontal asymptote. The x-intercept in this case is when the top equals 0. Well, 1 is never going to equal 0. So this graph doesn't have an x-intercept. Y-intercept, if I plug in 0 for x, then I would get 1/2. So I'll go ahead and mark my asymptotes. And this one, the whole and the y-intercept give us a pretty good indication of where this graph is going to be. So I'm going to have one curve in this top right quadrant because I have to hit that intercept and I have to go near that hole. And then because the x plus 2 factor is not squared, I'm going to go on opposite sides. But again, if I'm not sure, pick a test point. If I want to plug in -3, I can see that I get 1 divided by a negative, which tells me this region is negative. So if you're not sure, pick a test point and plug it in. All right, let's move on to our last two. Again, factor first. And this one's kind of a special case. So what's going to happen, you'll notice, the bottom factor is into x minus 5 squared. So x minus 5 cancels out, which makes us think we would have a hole with an x-coordinate of 5. But if I plug that into the remaining function, I get 6 divided by 0, which is undefined. Well, if it's undefined, it doesn't exist. This graph actually doesn't have a hole. The reason it doesn't have a hole is because at x equals 5, there's still a vertical asymptote there. So even though that factor canceled out, there's still a vertical asymptote at x equals 5. Horizontal asymptotes, look at the remaining function, same degree, divide the leading coefficient. And then x-intercept and y-intercept are the same as we've been doing. There's only one x-intercept. It's at -1, 0. The y-intercept, plug in 0, and I get -1/5. So we can go ahead and plot those. And I can see I've got my graph in this bottom left quadrant. And again, pick a test point or know that we're going opposite directions at that asymptote. All right, last one. We're going to go ahead and factor. That bottom, that is a perfect square trinomial. That factors into 2x minus 1 squared. So there are no holes on this graph. So this graph is just going to factor into, I have a vertical asymptote, only one, and it's at x equals 1/2. But if you notice, that factor is squared. Since that factor is squared, that means at that vertical asymptote, both sides of my graphs are going to go to positive or negative infinity in the same direction because that factor was squared. Horizontal asymptote, this is bottom heavy. X-intercept, top equal to 0. Y-intercept, plug in 0. And we'll graph our features. So I've got 0, -2 as a y-intercept. I've got 2, 0 as an x-intercept. So kind of hard to tell because it's on the axis. This graph's kind of weird, but again, using the information we know. I have a y-intercept in that bottom left quadrant, so I have to go through that bottom left section. Because we talked about how this factor was squared, that means my graph's going to go in the same direction on both sides of that asymptote. So I'm going to be going down towards negative infinity on both sides because that factor was squared. Then we get to this intercept. Well, that intercept, the factor that gave us that intercept, that wasn't squared. So I'm not going to touch that point. I'm going to cross through it. But even though I cross through that point, I'm still going to go towards my horizontal asymptote. So my graph does something a little special right there and just looks like that. Again, if you're not sure, pick a test point in all of your regions. Each region is in between vertical asymptotes and x-intercepts. So you would have 1, 2, 3 regions that you could pick test points for. And you would get positive, negative, and negative if you picked those test points. And your graph could also look like that as a result. All right, so that's it for rational functions. Next class, we're just going to get some more practice on these.